Thank you very much. It's a pleasure to be able to talk to you. I'm sorry I cannot join you live, but I hope this video will be as good. And let's get into the transformers. So I want to tell you today about Reformer, which is an efficient version of the transformer model that we've worked on recently. But before I get to that, I want to tell you a little bit more about the journey, about the models that led to the transformer itself, the reformer, and what I think the future brings for these models. So the journey starts with deep learning and NLP. What I mean with NLP is a number of language processing tasks, such as part of speech tagging, parsing, named entity recognition, language modeling, translation, and so on, that were studied for decades and way before NLP started at all. And they've been studied in many various ways, but even just a few years ago, the standard way to do them would be to have a stack of systems that analyze language. So we would take a sentence, tokenize it, maybe tag parts of speech of the tokens, try to do parsing, and on top of that, maybe do entity recognition. And these stacks were very complicated systems, and they achieved good performance sometimes. But they were hard to maintain, and they were very hard to add and change. So around 2013, 14 or so, deep learning came into the picture, and there was this paper about encoder-decoder models, or actually a series of papers, where people started claiming, like, you can do NLP by just feeding data to a neural network. And maybe these days it seems obvious that this is something you can do, but I want to impress on you how game-changing that was. Like earlier, doing NLP meant you had to learn a lot about the whole stack. Maybe you should have some linguistic knowledge. And it was like adding one blue score in a translation model was a big deal. And you could probably write a PhD about that, about the whole things you needed to build to do just that. So the idea that you can just train a neural network, and at the beginning, these were RNNs. RNNs, you probably know already, are these networks where you input things symbol by symbol, and you start with a go symbol and then output one word or token or letter. You feed it back in, output another. And the idea that you can train this network, which is mathematically fairly simple, you can define it on half a page, and get results that are comparable to all these systems that took decades of engineering, this was not very believable. And people were a bit skeptical, but, did it work? Well, it works very well. For example, in language models, the models people used were n-grams, right? N-grams, say 5 grams, it's like you take the previous 4 words, build the statistics over the data set, what's the 5th word, and that's your model. And the performance is measured by perplexity, and people had like 60, 50, and then the RNNs came, it's like the middle column, and it was 54. So some people in the NLP community were thinking, maybe it's better, but not that great. Maybe it's slightly better. And many people believed, on this data set, LM1B, you can't get below 40. This was kind of considered like that's the human performance, maybe 35. And then suddenly, a few years later, with not much other than scaling the networks up, we went to 30, 28, now we're at 23, or maybe even below. So progress happened without this huge human engineering. And the field that I was most involved in, which is machine translation, the performance, the shock was even bigger in the sense the phrase-based machine translation models that came before deep learning on this standard English-German translation set, they had performance of about 21 blue. So blue is a score used to measure performance, and it's quite a good score, at least at this range of scores. The human blue score of human translators on this data set is about 31, 32 or so. So the phrase-based models were 21, and people thought, okay, maybe we can get them to 23. That would be really nice. It was not thought that you could try to reach human parity. And the early LSTMs came, and they were about 20, 21, and then we scaled them up, the GNMT model, which was just a larger LSTM, and it got to 25, and people were extremely impressed. And that allowed us to actually launch this in Google Translate. But even then, part of the Translate team was still not fully believing that this is the future, because people were like, okay, it gets better results here, but does it really get better results on all languages? How does it perform in low resource settings? There was a number of questions. And then larger models got to 26, and that was great. But people were like, okay, maybe it's working. That was all based on RNNs, and RNNs operate like it's depicted here. So there's an encoder. It reads some words, let's say Chinese symbols, and it operates step by step. So it has a hidden state, reads an input, computes a function, say the LSTM cell, creates the next state, reads the next input, and so on until the encoder finishes. And then the decoder does the same, except it gets fed the symbol it generated previously. And these are very powerful models, and as you've seen, they did pretty well, but they're not very fast, especially on modern accelerators that are great for parallel processing. They can do huge batches and huge matrix multiplications. These models, they work fine, and you can optimize them and tune them to work even better, but they're not that fast. So what you'd like is something more parallel, preferably something that would process the whole sequence in one go rather than step by step. So that's the speed problem. And there is another problem that turned out to be actually more important, but I feel like at that time we did not appreciate it enough, which is, how about gradients in long sequences? So every step you see in this picture, every step that is made, includes a nonlinearity. So when the gradient needs to travel back from the end of the sequence, it needs to pass this many nonlinearities. And now in this model, you already have an encoder-decoder attention that was already around at that time, which is a shortcut of sorts, because the gradient can then pass through this directly to the encoder. But it cannot pass, for example, from the last word you're generating to the first word. So you have, if you're generating a sentence with n words, then you have at least n nonlinearities that the gradient needs to hop through. And you can say, well, but the gradient will not vanish because we're using LSTMs and they're long short-term memory cells. And this is true up to some length. So it's fine for sentences of length 20, 50 words. It can be made to work with 100, but when it gets really long, like thousands of words, then the gradient will not behave very well. It will be very hard, if not impossible, to train this model. Now you may say, if it has 1,000 words, it's not a sentence. So indeed, for sentence-to-sentence translation, it may not matter, but for doing things like paragraphs or writing books, it starts to be very relevant. So that's where we started when we were thinking about the transformer, how could we solve the speed problems and the gradient problems using the attention mechanisms in a better fashion. So the transformer is a model that doesn't have recurrence. That's why it's very fast and parallel, and it relies on self-attention. So what is self-attention? When you have the words in the sentence, each word will be attending to every other word in the encoder. And while it's doing that, it will gather information about other words and pass it through a feed-forward layer. And we'll have n layers of that. Say, at that time it was usually 6, now it's more than 1. And the decoder will be similar, except the words will only attend to words that came before them, because we need to avoid copying behavior, just knowing the future. So in this way, all of that happens in parallel, meaning the input is one big tensor, and the output, when training, is also one big tensor, because we know the golden truths for every word. And it processes them as if it was one feed-forward model. So it's really fast. And thanks to the attention mechanism, every word is just one gradient hop from every other word. So how does this work exactly? First, let me recapitulate that there are 3 kinds of attention, right? There is the encoder-decoder attention, which you already had in RNNs, where the sentence you're outputting is attending to the encoder sentence. Then there is the encoder self-attention, where every word can attend every other word. And then the masked decoder attention, where we are attending to the words that came before. Now, how does attention work? Well, you probably know convolutional layers, where every element can access a set of other elements, right? Say a field of 5 elements, and there is a separate weight for every one of those. So attention you can think of as an expansion of this, where every element can access a very wide field of elements, maybe all of them that are there, but there is not a separate weight for every element. It's a weighted sum of the vectors corresponding to them, and it's weighted by the strength of the relationship. So if a convolution is kind of like a positional lookup, you have a weight for position I minus 2, I minus 1, I plus 1, I plus 2. Attention you can think of as the lookup based on content. Your vector comes with a content, and it looks up this content in a set of activations. So how is it defined more precisely? Well, let's assume in the abstract setting that you have some dictionary of keys and values. Key 0 corresponds to value 0, key 1 value 1, key 2 value 2, and so on. And all of them are vectors in some d-dimensional space, say 512-dimensional vectors. Now a query arrives, and the query wants to look up a value corresponding to a key that's most similar to it. But of course, this is all deep learning. We want it to be trainable. So we'll do a softmax. Instead of picking the one most similar key, we'll check all of them out and pick all of those that are similar to the query, and pick values corresponding to that. Now, if you think that the distance function of the key and query that you care about is cosine similarity, and if you thought they were unit normalized, then the dot product of the key and the query would give you the similarity. Now, what turns out to work very well is to do exactly that, but without unit normalization. So we will take a softmax over queries dot product with keys, which in a batched setting is queries key transposed. It's a matrix multiplication. And we will not normalize them. And that actually helps the softmax, because with the length of the vectors, it can determine the temperature of the softmax. So it can be either very focused or a little bit less focused and act as a summing over the keys. So we take the softmax over queries multiplied by keys transposed. That gives us a matrix of size a length of keys by length of queries. So if this is a sentence, this is an n by n matrix. And we will come to this because later you will see that this is a problem because it's an n squared matrix. When n grows larger, this can be very large. And then we will matrix multiply it by the values, which will give us an n by depth matrix again of the corresponding values. The reason I write these equations here is I want you to focus on the fact that these are actually just two matrix multiplication and one softmax. And matrix multiplications are very fast on modern hardware. So that's why this attention mechanism is so nice, because in addition to making the gradients behave well through the softmax, it's also very fast to run. Now, as we said, the attention complexity is about n squared d. N squared n would be your length of queries and keys, and d is the depth, which is like, say, 512. So compare it to an RNN, which has a computation of about nd squared. Now, you may think, oh, nd squared is just linear, while n squared d is quadratic, so maybe nd squared is better. But remember that d is 512 in a base model, 1000 in a bigger model. So if you're doing just single sentence processing, like for translation, then n is much smaller than d. So you're gaining not only because you have very fast matrix multiplications instead of this stepwise thing that cannot be easily parallelized, but additionally, you have n squared d instead of nd squared, which is just smaller in a sentence-based setting. So that was all great, and you implement it, and of course, at first it didn't work. So what's missing? Well, self-attention, first of all, is a weighted sum. So it doesn't respect the order at all. It's a set operation. You could permute your words and nothing would change. So we'll handle that by adding a vector that says what is the word position. Okay, so that's handled. But then there is another problem that it has no trainable weights. So we'll have feed-forward layers, but the convolution has this nice thing that, maybe you care about the word that was just behind you, and you would like to multiply it by one weight, and you care about the words that was 2 steps behind you, and you'd like to multiply it by another weight. And with attention, you'll need 2 layers for that. So you would need as many attention layers as the width of a convolution field, and then that becomes impractical. And to solve that, you can do multi-head attention. So what is multi-head attention? Multi-head attention is basically doing a number of attentions in parallel, except transforming inputs and outputs of each of these attentions by a different linear matrix. So here's how it works. You have your queries, keys, and values again. You transform them with a different linear projection, and you have as many of them as heads. Then you do your attention on every of these heads, concatenate the results, and have a linear layer. It's super simple, but it really helps because it gives the model the ability to do in parallel a number of steps. So now, if you have this, you have your linear layers, so you get back your nd squared factor. So now you're not that easily faster than RNNs, but you have large parallelization because these are linear layers, like they operate position-wise. So they're really fast to run. That's how you arrive at the transformer model. So you have your input sentence, you add your positional embedding, do the multi-head attention, then we have a residual connections with adding and normalization. And in the original paper, the normalization happened afterwards. It's better if you put it before the input to the layer, but that's a smaller detail. Then there is the feed-forward layer, and that's a single layer of the transformer. And in the decoder, it's the same, except the self-attention is masked, so it only attends to elements that were before, and then it attends to the encoder. So there is the encoder-decoder attention as well, where the queries come from the decoder and the keys and values come from the encoder. And at the end, you have a linear layer and softmax as usual. That's the transformer model. And does it work? Well, it works spectacularly. So I told you before, doing 24 blue used to be a big deal on the English-German dataset. And really large RNNs went up to 25, 26. And then transformer came, and in the base setting, it did 27. And the big model did 28.5. And soon thereafter, there were models doing 29. And these days, you can almost get to 30, and we're basically reaching human parity on this metric, which is a different story from whether we're really reaching human parity on translation. But at least on the metrics, we are getting really, really good. While the training cost, the flops of the transformer are lower, so it's much faster to train. And okay, so you can say this is translation, but how about, as I said, are we really reaching human parity and natural language processing? Well, it's not that simple. It's not enough to train on an English-German data set. But there is this thing called BERT, which adds a new kind of loss to the transformer. So the model for BERT is actually just a transformer encoder. It doesn't even have a decoder. You just remove 15% of the words, and the task of the model is to predict them all in parallel. And BERT really gives you, when you pre-train it on a large data set, say large like all of the web, or as large as you can get, and then you start from this pre-trained model and start fine-tuning it on smaller data sets. That helps tremendously, and on a set of tasks that's called GLUE that were kind of developed to be hard for models, but for models before transformer, BERT reaches like 80%, which is the human baselines are about 87. And then there is Albert, which uses a recurrence in the layers of the transformer, and it gets to 89. So if you add recurrence to the layers of the transformer, and that means just that instead of having layer 1, 2, 3, 4, you just repeat the weights of layer 1. So it's like layer 1, 1, 1, 1, 1, say 20 times. And this helps the model generalize better. Then you're getting really good results on this task. And you can say, okay, so this is NLP, but these are sequence models. They could model arbitrary sequences. So how about other tasks? And actually, if you say, like, take a look at image generation, and when I say image generation here, I mean you're generating the image pixel by pixel. So this is not a very smart way of generating images. You're just generating the next pixel in raster scan order from the top to the bottom, from the left to the right, like that. And it works. It's predicting the next pixel, and it's predicting them quite well, in the sense that image transformer can fool people like making low resolution faces or boats. And these days, they've gotten better and can generate really nice images. You can do the same you can do the same thing as BERT, predicting missing things for protein sequences. And these models implicitly learn how proteins fold. So they're really useful for non-NLP tasks too. While in NLP, if you train large models, these transformers can generate really long text. So this is an example taken from the OpenAI GPT-2 transformer, which is just a transformer decoder model with some changes in nonlinearities. And so it doesn't have any input, it just generates the next word, right? you started with the prompt, like in a shocking finding, scientists discovered a herd of unicorns living in remote mountains, and the researchers were surprised that they spoke perfect English. And the model starts generating the follow-up to this story. The scientists named the population after a distinctive horn, blah, 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 some researcher. And you can see that this history is coherent even on the scope of paragraph after paragraph. So this is a testament to the fact that these gradients really can travel far without problems. Like attention can really jump hundreds of positions backwards, attend to something, and use it and generate the next thing. So that's really great. It's a really powerful model. And it's so powerful that people have started using it everywhere. There is even a company called Hugging Face that has a huge bunch of pre-trained models. So let me share with you a tab. So here is Hugging Face co-models, and they're kind of all transformers as far as I can say. And you see there's the GPT, GPT-2 large. And the nice thing on this website is you can kind of click on the model, and it even allows you to do inference. So here you start with some text, as exactly as I shown you on the slide, and it generates the follow-up to this text. So let's see what this will generate. So transformers have gotten really, really popular, and it's deserved because they work really well for NLP, and they even work for some other tasks. But as we've already said, there is this n squared problem, right? There is the problem that when n gets large, the transformer complexity is n squared. So as you see here, we generate a text. And it's some interesting text, but it took 14 seconds to generate only this much. This is probably because it may be running on some slow runtime. Nevertheless, if it's n squared for long sequences, if you take English-German, you can load some English-German model. This should be much faster. Yeah, it's a sentence-based model. It really works fast and well. And it's a great achievement that, can have a website just with research models that does translation. It's just great to see, that in the matter of about 5 years, the progress has been so enormous. But as a researcher, you've got to ask, how about these long sequences, right? There is this n squared matrix. If you have a sequence of length 1 million, million times 1 million will not fit into memory. So can we do something that these transformers, that all these great results could really work for long sequences? And that's where we focused our recent work on the reformer model. In the paper Reformer, the efficient transformer, we actually show that yes, indeed, you can get transformer performance without the n squared factor, without paying the n squared times d price, and instead paying just n log n. So what's the main idea here? As we've said, attention is a softmax over queries multiplied by keys. And what that means is we're searching for keys that correspond to the queries, and we're doing it in a soft way, right? And softmax is one mathematical formulation, but when the sentences are like 1 million long, we don't really care about summing over all of the million things. It doesn't need to be that soft. What we really care is picking the nearest neighbors of the query, so say 30 or so on nearest neighbors to the query, and just being soft over those. The other ones, well, they're there, but they're actually only disturbing the temperature of the softmax. So in some sense, what attention really is a nearest neighbor search. We have a query and we want to find the nearest neighboring keys in the vector space. Now, the great thing about nearest neighbors is that it's a problem that's been studied for a very, very long time. And we know there is a faster way to search them than searching through all of the candidates. So how does this work? If you have, say, 500 dimensional vectors and they're k1 to kn, these are your keys, and you need to quickly find the nearest neighbor to a query among these vectors. So you have the queue, you need to find the nearest neighbor. Well, you can compute the distances to each one and pick the best. Yeah, that's slow. Or you can do the following. You will put these keys into some random buckets, meaning you will assign a hash, which is a number, to every key and to the query. And this hash will have this property that it's locality sensitive, meaning with high probability, if two vectors are close, then they get the same hash. Now, how can that work? You're like, okay, well, if you assign a hash to something, it's kind of random. Why would close thing get the same hash? So here is the most basic idea of locality sensitive hashing. Imagine you have just points in two-dimensional space. So here on the right, you see there is a number of points. These are the round dots. And you cut this space by 3 random lines. So now you've cut this space into a number of subsets, and we made a color for a different subset, right? So there are the things on the left of one line, and so on and so forth. And imagine the hash is the color, meaning it's the subset of space. So if you have a string of bits, the bit is 0 if you're on the left of H1 and 1 if you're on the right. The second bit is 0 if you're on the left of H2 and 1 if you're on the right. And the third bit is 0 if you're on the left of H3 and 1 if you're on the right. Then every point gets a hash, which is this triple of bits. And as you can see, like if 2 points are very close by, then with high probability, they will get the same hash because they'll just land on the same side of all of these random lines. Now, this is not perfect, right? This is a probabilistic algorithm, and you see here like this one point, which is kind of in this middle triangle, and its nearest neighbor is not necessarily another red point, right? There is another one because we've cut it off. So it's a probabilistic thing, and just doing this once is not enough. So what you need to do is you hash once, you get these hashes, you search for a nearest neighbor within your hash. So you see you only search within this part of colors, which may be much smaller than all of the points. And then you redo it with another 3 random projections, right? So you use the randomness. You redo this a few times. This is the number of hashes that you need to do. And with high probability, your true nearest neighbor will be somewhere. So we'll use this idea to do an LSH attention. So we'll try to approximate this softmax that attention does by hashing, meaning we will hash queries and keys and only check for those that fall in the same bins and repeat this a few times to increase the probability that we hit the right thing. Now, one thing to note here is that, hashing works, this LSH hashing really works best if you have one set of things, while here we have queries and keys. So, and also, yeah, I think this is better to see on this picture. So we have queries and keys, and what we will simply do is we'll assume that queries and keys are the same. And as you'll see later in the transformer architecture, you can actually assume that, and it makes no difference to training. So this is helpful in an implementation. And this LSH attention works as follows. So you have this sequence of queries, which are the same as keys. You assign the color, which is a hash. So each blue thing has the same hash, each yellow thing has this other hash, and so on. And then we sort them, and we sort them in the following way. The most important thing we sort by is the hash. So blue is 1, yellow is 2, red is 3, and white is 4. But within the hash, we maintain the order that was previously. So things that were before each other are before. Okay, so now if we were true to the math of hashing, we should look within each color. Now, as you see, these buckets can be of very different sizes. Like one can be 6, one can be 3. And on modern accelerators, like analyzing things of such varying sizes is not very efficient. What is efficient is analyzing things of size 128. 128 is a very good size to operate on. So we decided to just do this, meaning we split this thing into chunks of a certain length, 6428, right? Now, okay, so you say when we did this, we may have some overflows, like some chunks, like you see here, some has 3 yellow ones and 1 blue one. So that's not okay. This blue one should look at the other blues, while the yellows should not look at the blue, right? To do what we wanted to do. So we will achieve this by looking at one chunk back always, and within a chunk masking out the things that have a different hash. So this achieves the thing that you see at the bottom. And now it may still be incorrect because we may overflow to more than one bucket within a hash bucket. So we may miss some attention if one hash has too many elements. But we have the sorting with respect to time, so we will at least get the most recent elements, even if we overflow. And we try to do hashing so we don't overflow. And it actually learns to not overflow much. So that's the LSH attention. And now what's its computational complexity? It's n log n. I will not go into details, but that's how it works. So great. So now we have an LSH attention transformer that has this n log n complexity and attention. But if you look, so okay, n log n, this is doable for a sequence of length 1 million. Let's run it. And if you try that, you will see that you run out of memory. You run out of memory during training because if you have n layers, then you need the big N, then you need big N times small n times d memory. So if small n is 1 million and d is 1,000, then that is already 1 billion, meaning the activations take 4 gigabytes, right? 4 because you have 4 bytes per float. So even just one activation sequence for the whole input takes 4 gigabytes. And if you have 6 layers, that makes you run out of memory. But these layers, you should need memory per layer. And you could help this by doing recomputations. But what we did is using reversible networks. So in a standard residual connection, you just do y1 equals x1 plus f of x1, right? And then if you have another residual layer, you have y2 equals y1 plus g of y1. And in transformer, the f is attention first and g is the feed-forward layer. Now, in a reversible network, instead of having one vector, you will have 2. So every activation will be split into 2 vectors. Say x1 and x2. And what you do is you use only the first half for the first part and the second half for the other. So y1 becomes x1 plus f of x2, while y2 becomes x2 plus g of y1. So as you see, x1 does not flow to y2 other than through y1. Now, why is this so smart? Well, because just by reverting the signs, you can recompute x1 and x2 from y1 and y2. So it's reversible. How do you recompute it? Well, very simply, you start in the second equation, you just move x2 to one side and gy1 to the other, so you get x2 is equal y2 minus gy1, can be computed solely from y's, and then x1 is equals y1 minus fx2, and fx2 you've already computed. So you can recompute x1, x2 from y2, so when you do your backwards pass, you don't need to store the activations waiting for the gradient. You just recompute them. So Reformer is a transformer model that uses LSH attention and reversible layers. And its memory use is just n times d. So it's the length of your sequence times your embedding depth. You don't need to recompute anything else. And this model is as good as a baseline transformer. So we ran a number of experiments. As I told you, you can have shared queries and keys, and it actually trains as well as when they're separate. You have the reversible layers, and you can do that separately from changing the attention. And as you can see, it trains basically the same as a non-reversible model. And the LSH attention has a parameter which is how many times do we hash. And if we hash just once, then it's not as good as full attention. Even if we do this 2 times, well, it's a probabilistic algorithm. It doesn't find the solution in just one go. So the blue dots are when you have 2 hashes, and they're a fair bit worse than the full attention, which is the bottom gray thing. But if you go with more hashes, it gets better and better, and already 8 hashes is very similar to the full attention, while with 16, you start matching it. Now, this costs you a bit in speed. Like 16 hashes is 16 times slower than 1 hash, which can slow you down a bit. But as you can see, you can do 8, and it's already good. And why this doesn't matter all that much is this plot, because of course it's n log n versus n squared, right? So, and this really works in practice, meaning the rise with sequence length of the time you need for a reformer is much slower than you need for standard transformer. So a reformer can run on sequences of like 100,000 tokens on a normal 8 GB GPU. Actually, if you optimize it, you can even fit 500,000 on an 8 GB GPU. And so it's a wonderful model that can do really long sequences. And we implemented it in a library called Trax, which I'll tell you about a little bit more in a minute. But if you want to try it, so for one, there is an illustrated reformer tutorial that you can go and learn more in an illustrated way. And there is a reformer model in the Hugging Face library, and they even made this collab which explains their PyTorch code in all detail, including some details that we didn't even include in the paper, like axial positional encoding. It's a 4-series collab, so it explains the self-attention, it explains chunked feed-forward layers, which I didn't talk about, which improve memory use, the reversible layers, and positional encoding. You can check it out and see how you can really fit 500,000 tokens in 8 GB of RAM. And the way we implemented it is in a library called Trax, which we developed with a number of people. Trax is a successor to the tensor-to-tensor library, which is the library which we developed with the original transformer model. And so tensor-to-tensor started as a library quite similar to what Hugging Face is now, but without pre-trained models. So we tried to make a standardized interface to datasets, model architectures, optimizers. We tried to make every model work with every dataset, and make it a nice library, hardware agnostic, and so on. 2 years later, there were problems with tensor to tensor. It was very hard to maintain. That was our main problem. We had a number of issues. On GitHub, we stopped responding to them because we were overwhelmed. And it was really hard to debug. It was written in TensorFlow, and it had this interface to make every model work with every data that was a bit weird. It was called modalities. And for example, the inference code, it was really fast, but it was really hard to read and maintain. So we thought, okay, we should reduce scope. Like for data sets, there are no libraries like TensorFlow datasets that can provide you a dataset. But the more important thing is, like, we decided, okay, let's use a different API for the models. So TensorFlow became eager in the meantime, so that already helps debugging. But what we wanted to do is build something that can allow you to understand what's happening in the model from the bottom up. So you can read the code and actually get to the point, like, what is happening there. And to me, the best way to do this is to just use NumPy, because NumPy is like the denominator that everyone understands. You need to learn what NumPy functions mean to understand algebra in Python. So could we do machine learning with just NumPy? And if you think of it like what we write in papers, right? Attention is a softmax of Q key transposed values. Multi-head is like concat matrix multiply attention. Or here it's the Adam optimizer, right? It's get gradients, multiply, assign. So what you see here is, like, we have basic maths that can be expressed with NumPy. We have tuples, list functions, so that's Python. And we need gradients. Of course, for deep learning, we need gradients. But all other things don't look so fundamental. So could we do this with an API that just has NumPy functions and a gradient? And this is an API that is in a library that's called JAX. So Google JAX is a library that's built for deep learning on top of XLA, which is the compiler underneath TensorFlow, that uses a NumPy API and provides you with gradients. So you import NumPy from JAX and provide gradients. So that's the idea to use that we use in Trax. It's the NumPy API with gradients. And this is actually taken from the code of Trax. And you see on the right side, you have a screenshot from the Adam paper. G are the gradients, then M is like beta times the previous one, and so on. And here you have the real code in Trax. It's not cheated, it's not simplified. It's what's real used in the implementation. And you can very easily see the paper in the code. And this has been a problem to me, that in many papers, and it actually happened to the original transformer paper in Tensor to Tensor, that after some time it was very hard to find the paper in the code, because the code has just grown around and included a lot of tricks and speedups. So Trax is a library where we try to go really clean, so you can find the model in the code. And this is actually the transformer language model, just the decoder part. And you see, there's a shift right, there is a decoder block, layer norm dense, and there's embedding, dropout, positional encoding. It's really easy to go from the paper to the code. So that's the goal with Trax, and that's where we implemented Reformer, and I think it's still reasonably readable, and it runs at top speed. So where does this leave us? Well, what does running transformer models on 1 million tokens buy you? You know, we've managed to solve this length problem, but what does it mean? And I think this means many interesting things. I think this means generating images, music, or even small videos with transformers will become possible, and that means will generate great things, right? We can train on data sets of whole books and start generating them. And it will be very interesting to see how the models maintain or don't maintain context. Do they make their own stories? Do they make, what is it what they produce? This will be great to see. But there's even more interesting things. So recently there is this GPT-3 model from OpenAI, and this model shows that you can just train a model on all of the web, and then instead of fine-tuning on certain tasks, so training again, you just make the task part of the input. So if your training data is very small, say your training data has just 20 examples, then it becomes just part of the input and the model continues from there. So you see training examples are this, and now solve me that. And it works with large models. So, but this is limited to training data that's short because they use transformer that has the n-squared problem. So maybe with the transformer that can handle 1 million token, maybe your data set can become part of the input. And in general, why do we, when should we train and when should we just have a data set be part of the input is an interesting research question that I think will help us build models that generalize much better and do much better one-shot learning. And finally, I think this will have great use in reinforcement learning, because in reinforcement learning, you really should look at the history of your interaction with the environment when it's not purely Markovian, especially, or you have some hidden variables, and then apply a model to it. So I think this opens up a lot of avenues. And also, I'm happy that we built Trax as a library where we try to stay really clean and close to the math. So you can really read the code and get the idea of what the models are, what the optimizers are, while still running at state-of-the-art speeds and running on GPUs, multi-GPUs, TPUs, and so on. So that's what we've been working on, and I hope you like it, and I hope you'll take the reformer for a spin and try to apply it to many tasks or improve it to make it even faster. And I hope you'll get great results with it. Thank you very much. Bye.